All right, class, it's time to get started with chapter 4. So in this chapter, we're going to discuss pretty much the same things we discussed in chapter 2, well, 1 and 2. Except for now, we're going to be dealing with functions of more than one variable. So we will learn how to take derivatives, how to use them to find minimums and maximums, and solve optimization problems. Basically, why do we need a function of more than one variable? Well, just assume that a company is producing more than one item, right? So it produces X amount of item A, Y amount of item B, and so on and so on. So we don't need to make things too complicated. Once we know how to deal with a function of 2 variables, then sure enough, we'll know how to deal with a function of 3 variables. But as you will see in the next chapters or in the next sections, things blow out of proportions quite fast. So I'm just going to save it for 4.2. You'll see what I'm talking about. So what is a function of 2 variables? Well, as I said right here, a function of 2 variables. So as I said, we could just look at 2 more, but really most of the time we will be concentrating on functions of 2 variables. So it's a function so that for every input, now this time you have 2 variables that you're inputting, not just an x, but an x and a y. And you plug those in and you get one value. So we're not going to call it the y value anymore. As a matter of fact, we call these the z values because we used a y as one of our variables. So the inputs are ordered pairs, a value for x and a value for y. The outputs are one number, one answer, a single real number. The domain for a function of multivariable is still the same. It's the set of all possible inputs. So what can you put in for x and what can you put in for y? And the range is what comes out of it. So if you plug in these x and y values, what sort of numbers can you get? Yes. Now, the question really becomes, what will the graph of a 2 variable function even look like? Well, as I said, you now need a what? You need an x value and a y value just as your input, right? What does that give you? A value z. So you have really a 3-dimensional problem that you're looking at. X and y are your inputs and z is the answer for that. So what you will get is a 3-dimensional shape, okay, which is very hard to draw on a 2-dimensional piece of paper. So we kind of get to, we're not going to be graphing these functions. I'm telling you that. It's just not going to be as easy. So, yeah, that's it. And of course, same as this, what we will want, again, we're not going to graph them. It gets too complicated. But what we will still want to do is do what? Take derivatives, find minimums or maximums. So definitely even on the surface like this, you guys could kind of tell where a minimum or a maximum possible high value might come up to be, right? So the min kind of looks, this might be the lowest point. The highest point looks somewhere here in the middle of the surface. Okay, again, I'm kind of trying to look at it as a 3-dimensional shape. Okay, so for the first section, it's pretty easy. All we're going to do is just get used to these type of functions really quick. So what I want to do is kind of bring back some stuff that we talked about. It's not much of an issue to find the domain of a multivariable function, but I'd like to do that anyhow, because you need to know what sort of values you're even allowed to plug in here. So the reason I brought this up is because if you just remember from what we learned in chapter 3, logs have restrictions. So what we know, I'm going to think again about the domain of this function. So what we know is that what? Whatever you put inside the log has to be positive. So sure enough, out of this immediately comes up that x must be greater than 3. Yes. And then the y value is the same because this quantity 2y plus 6 must be greater than 0. So if you solve this, minus the 6 divided by 2, y should be greater than negative 3. Yes. So the domain of this function will easily come out to be all the ordered pairs x comma y. So you can only plug in x comma y values where what? The x's are more than 3 and the y's are more than negative 3. So that's all that you're allowed to plug in here. Okay, well, let's plug in something. So if I'm going to ask you to evaluate f of 4, 0, am I asking you something that is even possible? Sure, x's are more than 3, the y's are more than -3, so that should work. So I'm going to plug this in place of x, I'm going to now put a 4. In place of y, I'm going to put a 0. And sure enough, I just have to put this in my calculator. That's an ln of 1, which you all know is 0. And then an ln of 6, which fine, put in your calculator or not, that's about 1.79. Okay, so it works just the same as you plugging in values in a function of one variable only, except for now you just have to plug in 2. So let's try one more. What is f of 27 -2? So it's natural log of 27 minus 3 plus natural log of 2 times -2 plus 6. And again, note that 27 was more than 3 and -2 was more than -3. So that should work. So that's an ln of 24 plus ln of 2. Put it in your calculator. So it says that that's about 3.87. Okay, fine. All right, let's try another problem. And again, I brought this up because this is also a function that has a restriction. And what is the restriction of it? The restriction of it is that x squared plus y squared, the quantity inside the radical, has to be greater than or equal to 0, right? You can't take square roots of negative numbers. And again, you can, but not when you talk about functions, because functions are to be graphed on the xy plane, and we can put imaginary values on that. Okay. All right, so the thing is, though, when is x squared positive? Always. When is y squared positive? Always. You add two positive numbers, not positive, it could be 0, because if you plug in a 0 for each of these, you will get a 0. So I'm just going to say that that's always true. No matter what you're going to plug in for x and y, once you square them and add them, you're going to get something that's greater than or equal to 0. So the domain for this function is surely all the ordered pairs x comma y, such that, that's how we read this bar, we call this the roster, not the raster form, the set builder notation, such that what, x and y are real numbers. So you can put in anything you want. Okay. All right. So let's plug in whatever we want. What about 0, 0? Well, that's the square root of 0 squared plus 0 squared minus 2 times 0 times 0, and of course that's nothing but a 0. Let's plug in -3 and positive 10. So that's the square root of -3 squared plus 10 squared minus 2 times -3 times a positive 10. So that's 9,109, whatever the square root of 109 might be. And that's plus 60. So I'm just going to leave it some kind of value, but it definitely works. Okay. All right. Okay, so easy, just plugging in values. All right, one more. What would be the domain of this function? Just going to write it down. It's the set of all ordered pairs x comma y such that what? What are the restrictions? Well, whenever you have fractions, you need to make sure that you're not plugging in 0, yes, in the denominator of a fraction, so that's that. And then the same thing for y. Y should not be 0 because 0 to the 4th is what gets you a 0 on the bottom there, right? Okay, otherwise plug in whatever you want. So let's plug in a 2 and a 2. So that's 1 over 2 plus 2 over 2 to the 4th. So that's a half. Plus 1 over 16, I'm sorry, 2 over 16 is 1/8. So when you add these up, you're going to get a 5/8. Okay. So easily done. I don't want to waste more time with plugging in values. Let's try this last problem here. Are there any restrictions on this exponential function? Any that you can think of? Or is there anything that I'm not allowed to plug into an exponent? The answer is no. The domain of an exponential function is all real numbers. the range is positives only, but that's not what I'm asking, right? So let's plug in whatever we want. And so let's plug, and by the way, you might have noticed that this is now a function of 3 variables. So I better give you, we call this a triple, an ordered triple. Okay, so I'm gonna get an e to the 2 times 0 minus an e to the 0 plus a 2e to the negative 0. Well, that's all of 0. E to the 0 is 1. E to the 0 is 1. 2 times e to the 0 is 1, so we're going to get a 2 for an answer. Okay. All right, let's try one more. 1, 2, and what did I choose here? Negative 3. Okay. So that's an e to the 2 times 1 is 2, minus an e to the 2. Oh, how convenient. These are going to go away. Plus 2e to the negative 3. So good enough, these are going away. That's a 2e to the 3rd, which you, by the way, can leave just like that. You don't need to put in your calculator and come up with an answer. This is the exact value, by the way, because as soon as you plug this into your calculator, that's just an approximated value anyhow. Okay, but either one works fine. You can leave either one of these answers. Good. And finally, this is a short section. We're going to have an example here, a couple examples of functions of multivariables. One that you're going to see coming up over and over again this chapter is what we call the Cobb-Douglas production function. So Cobb-Douglas production function is a function that's used to model the output of a company or a nation or anything really. It is called the production function. So what we mean basically is what? The production function simply tells you how many units are being produced. Yeah? So how much can this company or this nation produce, okay? All right, well, what does that depend on? So the Cobb-Douglas function specifically looks at this production in terms of labor and capital. And what do we mean by labor? Well, as I put here, work hours, right? So labor means how much are you paying your employees? Like how many employees do you have and how many hours do they each work a week, right? So basically the salaries you're paying out, right? So the capital means the units of invested capital, including buildings, right? So you maybe had to build something where you house your factory, the equipment you had to put in, materials you have to put in what you're producing. So putting all this together produces you the units, right? So again, how much you're producing depends on what? How many workers you have, right? How much money can you spend on, you know, putting out the materials, putting out the work hours, right? Putting on the machinery. So the more obviously you can invest, the more you can produce, okay? So the Cobb-Douglas function depends on these two units, and it looks at it this way. And what you see here is, and that's not by mistake, usually these exponents will always have to add up to 1. That's why I have a b and a 1 minus b. And then this value a is usually always a positive value, okay, some number that, again, it depends on. So again, p gives us the amount of units that can be produced if we are using L units of labor and K units of capital, okay? So that's what this story is about. Good. So all we're going to do for now, we're going to learn to take its derivatives, find a maximum as usual and everything else. But what we want to do for now is just what we've done, evaluate it. So as you see, these exponents here add up to 1, yes. So it just simply says plug in 230. So sure enough, we'll need a calculator. 200 to the 0.3 times 30 to the 0.7. Plug that in and you're going to get about 53 units. Okay, so in other words, what does that mean? When 200 units of labor, in other words, maybe hours, right? So you have, I don't know, 50 employees, each work 40 hours a week of labor. and 30 units of capital, and that doesn't necessarily mean $30. Maybe unit of capital is $1,000, right? So that's why we're saying units, whatever your company is using. And 30 units of capital are used or invested. The company produces 53 units. Okay. All right. And one last quick example here. It says it costs a furniture company $15 to produce each chair and $90 to produce each table. Fixed costs are $1,000. Find the company's cost function and find the cost of producing 60 chairs and 15 tables. Well, that should be easy. So our cost function depends on two quantities: the number of chairs and the number of tables. So as you see, it's a function of two variables. Okay, all right. So what does it cost? It costs $15 for each chair, so that'll be 15x, plus $90 for each table, so that'll be 90y. And then the fixed costs that we're adding on that don't depend on x or y are 1,000. So just as simple as in the last chapters or so, we were setting up cost functions that depended on one quantity only. Yes, it's just adding it on, so no big deal. So now, what would be the cost of producing 60 chairs and 15 tables? Simply means to plug in 60 and 15. Don't forget the 1,000, yes, for the fixed cost. And then you're going to plug all this in, and you're going to get a nice cost of $3,250. Okay, all right. So that seems like a lot, but again, it's because of the fixed cost. So the more you're going to be producing, that fixed cost will stay the same. So that'll make sense. All right. Well, that wasn't such a bad section. I hope you all can easily solve your homework now.